Have we just about got everybody back? You can hear me okay? Okay, so we were able to troubleshoot at least 3 problems, and now this is running just fine. I'm going to be on a different server though, and I'm on a different network, but this is running fine. I left off showing an exercise. I think that in the interest of time, these exercises will be left as homework. I'm going to be around till Sunday. I'm taking off a late morning Sunday. So if you want to get any sort of office hours or help on any of the exercises, I'll be around the whole time.
So you have the account, you can do it anytime, and Paco is here. Okay? So that is...
Okay. Any questions coming back from break? Okay. Let's see here. I'd like to show just a brief tour of the API to give some ideas of what can be done with Spark. I'm not going to dwell on the individual calls too much, but give some idea of what's in the API. The first thing is that there is a Spark context object, and all of the API hangs off of Spark context. So we'd shown this inside the notebooks. There's already a handle that's instantiated. It's called SC for Spark context. And that's both in Scala, Python, as well as R, etc. One of the parameters for Spark context is called master, and master will point to what cluster resources you're using. So if you're running locally on a laptop, you would probably see master being set to local star, and that'll say run locally with all of the cores on your laptop. If you're running on a Mesos cluster, you might see this kind of URL pointing to a Mesos master, or if you're running it in high availability mode, you might see a Zookeeper quorum kind of URL. On a Yarn cluster, of course, you'd be pointing to it. Or in Spark standalone, there's also, this is what you'll see out of the cloud notebooks is they're running on Spark standalone, whereas Spark itself is managing its own cluster. When we take a look at how the communications work between driver, cluster manager, and worker, the client side is where the Spark context lives. That would be on your laptop, or that would be inside the notebook. And that's talking with the cluster manager. It may be Mesos, it may be Yarn, or something else. That gets resources from the cluster to be able to run different workers. And on each of the different worker nodes, there is an executor process. And that process is really what does the main work. The executors are what maintain the cache. They also are the ones that run the tasks. And they also talk with each other. There's peer-to-peer communication among the executors, and that allows for certain types of data transfer to happen much more rapidly. We talked about RDDs, and so you can take some type of collection in the language that you're working in, whether it's Scala or Python or whatever, and you can parallelize the collection, like we'd shown before. We took an iterator and parallelized it. That's one way to create an RDD. Alternatively, you can point to a URL and then take a data set that's inside of HDFS or Cassandra or HBase or JDBC, a lot of different types of distributed data management. Now, once you have an RDD, there are really 3 things you can do with it. One is you can apply transformations, and transformations are lazy. They don't get evaluated right away. You can apply an action, which says, give me the result right away. The other thing is you can declare what type of persistence needs to be used. How is the RDD to be cached? And there's a number of different settings for this. I'm going to skip through that. Transformations, I'll take first. Transformations are lazy. So when you specify a transformation, then you're just building out the graph. You're building out the DAG of what needs to be calculated eventually. And the lazy evaluation allows for 2 types of properties here. One is it allows us to optimize. We can move predicates around the graph. So we can take and push a predicate further out to the edge. So for instance, if you were doing a pipeline with a large join and then some type of filter downstream from that, by doing lazy eval, Spark can take and move predicates around. It might make more sense, it might be more efficient to take and move that as a filter scan all the way down into where the data is residing on disk. So if you're using Parquet, for instance, it will allow for filter scans and a lot of predicate movement, and you get huge performance increases as a result. The other thing that the lazy eval gives you is a way to have fault tolerance, have recovery from lost partitions. So if you can think about a lot of these distributed storage frameworks have data replication. So if you're using HDFS, each partition of data is replicated in a few different neighbors. If you lose one of those nodes, then recovery is as simple as just going to one of the neighbors, grabbing that partition of data, and reapplying the graph at that point. So by virtue of having lazy evaluation, we get both the fault tolerance and the optimization. So some of the types of transformations we've seen, map and filter, flat map, which we had used earlier, such as in word count. Sample is another one. You can take and sample from an RDD with or without replacement. You can take and do a union. If you have if you have two RDDs, let's say, you can union them two at a time. If you have two RDDs that have the same schema, you take the union and you get one RDD. Because of the lazy evaluation, then a lot of this just passes through. This is really useful, for instance, if you're doing Spark streaming and you have different RDDs representing different time periods, you can take a union across those and build up a longer time window. You might have some data that's real time and some that's historic. You take a union of them and apply the same processing. Or you might have multiple receivers, different streams that you take a union of. Distinct is like doing a distinct in SQL. It's a way of finding the unique elements in an RDD. Now, a lot of the transformations that we use are based on key values. A lot of the more interesting aggregations at scale all require key values. And so there's a couple up at the top. Reduce by key is the one that we had shown used in word count. And reduce by key is what you typically prefer to use. There's also a group by key, and group by sounds familiar, but it's not really what it sounds like. Group by key actually forces all of the data for a given partition to fit into in one iterator in memory. You can actually get out of memory errors by using group by key. So it's really only useful for certain types of edge cases. Typically use reduce by key. Reduce by key will require some properties of the function that's being called. I'd mentioned that in word count, it's a monoid. So it's it's associative binary operation. Sort by key, join. Actually, join is a subset of cogroup. These are the large kinds of things that you do at scale a lot. And again, they require things to be shaped as key values. There's a lot of different flavors of join. There's different semantics, whether you're doing inner joins or left joins, hash joins, etc. The one that we'd shown in the earlier example was just a very simple inner join. You could also do a cross product. You could do partitions. And that's a way of getting around certain types of joins, making them more efficient. But these are just some. These are the more common ones that you'll see. These are all transformations, so they're all evaluated based on lazy evaluation. Actions, though, are what cause the graphs to be evaluated. I don't think we'd shown a reduce yet in any of the examples, but it's similar to the idea of a reduce in Hadoop. And this does require that the function inside is both commutative and associative. And that way you can do the reduces in parallel. A collect and count, we'd shown those. Another thing you do a lot is to say take. So you could say take 2, that'll give you the first 2 elements out of an RDD. It's kind of like doing a limit in SQL. First is an alias for take 1. Or you could do take with sample. And that's a good way, as you're programming, just to build up some kind of pipeline and see what do those elements look like. It's a good way to debug things. Now, typically, if you're working at scale, you don't want to do a collect with a terabyte of data. You don't want to take a large amount of results and drop them onto your console because it'll run out of memory. So typically we do saves in parallel. So there are actions such as save as text file, save as sequence file, save as Parquet, save as JSON, a number of different types of serialization formats, but they all do parallelized writes. That's typically what you're doing. Another thing is you can do for each, which is to say that it's an action, it'll take a function and apply it to all the workers, and then it'll iterate through the results. It's a way, for instance, if you want to pretty print a report at the end of a pipeline. For each gets used for things like that. Okay, so those are different types of actions. Persistence is what we talked about in terms of caching. And there's a few flavors of this. By default, the cache function that I'd used before is memory only. So what that says is store the RDD as deserialized Java objects. If they don't fit in memory, the partitions that aren't able to be cached will be recomputed on the fly every time they're needed. And this is the default. So what this says is that if I can't fit the whole RDD partition into memory on a worker, then I'll just recompute the parts that I don't have. And this is an interesting trade-off. If you look at the different generations of hardware, back in the 90s, networking became so much easier because of internetworking. And it was easier to manage a lot of distributed computing by reference across the network. So you had things like World Wide Web, you had a URI, and you could refer to some data set that lives out over there. In the 2000s, disk became very cheap, and so it was better to build distributed file systems with replication. And you just have a number of copies of the different data partitions on your file system. And then when you get into the 2010s, you had multi-core and large memory spaces. And so for some types of workloads, it becomes much more efficient just to recompute the results rather than go back to disk or go out to network, because those cost orders of magnitude more time. So that's the default with Spark. Now, it may be that you have a very complex pipeline and you have some processing that's, I don't know, order n squared. You don't want to recompute that part. Right, so that's why we have different trade-offs. So instead of doing recompute, you could also do memory and disk, which says take the objects, if they don't fit in memory, store the partitions on disk, local disk, and then read them back from there. And this is like with Hadoop, if you're familiar with chunking or spills, this is effectively doing spills. You could also do a trade-off between serialization or managing the cache with deserialized objects. Basically, you can trade off CPU versus memory. Because there's a lot of overhead to serialization. You know, if you have if you have a gigabyte of text on disk, and then you bring that up into JVM as string objects, it's going to be a lot more than a gigabyte in memory. Actually, substantially more. So sometimes you want to make that trade-off. You can also you can force it to disk, which is sort of the default behavior in Hadoop job steps. You can also choose to have memory replication. It's not used very commonly except in streaming. So when you have a streaming cluster, when you first bring the data in off a receiver, it'll do replication in memory so that you don't lose any piece of data. There's also another mode called off-heap that's still experimental. It's been used in Tachyon, and it will be used in other things, Tungsten and others. But the idea is that you can take your RDD and cache it out into some store in memory. And that way, multiple applications can share RDDs. Question?
So I suppose, making these choices is very application dependent, right?
Yes.
You sort of need to kind of have an idea what happens under the hood.
Yes.
So are there profiling tools that let me examine a particular type of RDD and sort of see, well, it spent that much time?
Yes. Yes, exactly.
Swapping and
We'll take a look at some examples. There are really two things there. One is I'll drill down a little bit later into the console and show a large application running and see where the bottlenecks are. So we can start to see what are indicated in terms of the amount of working set memory, how can we tune the cache, and also what's indicated in terms of other types of resources being used, disk, network, etc. So you can get that feedback. The other thing is that if you're working at a higher level, not just individual RDDs, but if you're working at the data frame layer to specify your applications, basically doing SQL queries, then Spark has more information, has more metadata about what you're trying to run. So some of these trade-offs are beginning to be made automatically based off of the feedback from the metrics along with the metadata at a higher level. That's sort of the longer picture of this.
So you can say, like, when you are working at Spark SQL, you can do cost-based analysis.
Yes.
So you can use that.
Yes, very much so. There is an optimizer called Catalyst. We'll go over that in just a bit here, actually. Question, yes?
Actually, one of the questions I usually receive is the performance of the Spark when it works out of code. So when the memory is full,
Right.
how is its performance?
Well, so that depends. It depends what type of trade-offs you're making. But if you had done spills, like for instance, if you're doing Hadoop and you're doing a very, very large join, you can't do all the right-hand and left-hand side of the join in memory. So with Hadoop, what typically happens is you chunk through the data using spills. So you take your intermediate results and drop them to disk. And so Spark has a similar kind of mode where you can manage the spills. And in which case, you're still going to get better performance typically than Hadoop because you don't have as many synchronization barriers. You don't have as many wait states.
Have you done any comparison between Flink and...
Oh, between Flink. I haven't. I know that in some cases, I know the default settings on Flink can get you some really good performance. I mean, definitely side by side. There are things that Flink can do faster. And I really like what they're doing on, what is it called, the deltas?
Yeah.
Yeah, there's some great design patterns in there. I think the two projects could probably learn from each other quite a lot. Yeah, and that's a good point. Okay, two other things in Spark that are not RDDs. One is a broadcast variable. So if you look at this here, I'm going to say sc.broadcast, and I have some type of object inside there. So effectively, a read-only copy of that object is going to be broadcast across the cluster. Now, the worker nodes have peer-to-peer communication, so they can actually talk to each other. So there'll be sublinear rates of sending this out. But this is good if you had, say, an anti-fraud model. You could create the fraud models someplace and then broadcast it across your cluster and do the scoring at scale. This is useful for maintaining state across a distributed algorithm as it iterates through a number of generations. Broadcasting state is something pretty common. So you get a broadcast variable, and then to access its value, you just say .value. This is similar to working with distributed cache in Hadoop, but a little bit more generalized. There's also something called accumulators, and this is a type of variable that has an associative operation. So it's a lot like using a counter or a sum, but much more general. You can take and subclass it and create much more complex operations, much more complex types of data structures. So this is a way of having out-of-band data. The idea is that I'll say sc.accumulator, and I'll give it an initial value. And then I can access the accumulator, accum.value, do some sort of operation on it. For instance, in this case, adding numbers to it. The operations happen out in the cluster, but reading the accumulated value only happens on the driver. If you try to access the value out on the cluster, it'll throw an exception. Because the accumulators are based on partial aggregates, and none of the workers can see the full value. This is really useful if you have edge cases. Say that you're going through 100 million customer profiles, and there's some small fraction of a percentage that are corrupted. Rather than throwing exceptions and stopping the whole pipeline, you could just accumulate the user IDs for the ones that are corrupted, and then have a report at the end. Or it could be used, I see this in certain machine learning algorithms, where there are particular things that need to be measured that are not part of the data flow. Like for instance, I can see this if you're building a random forest or other types of distributed algorithms. There's a great talk by Matei Zaharia about using broadcast and accumulators. It's from a few years ago, but it's still very relevant. And finally, for the API, a lot of Spark uses key-value pairs, and something that's odd is if you're in Scala, it's using the tuple2 object. and tuple 2 is ones based. Almost everything else you do in Scala is zeros based.
I don't know why they do it this way.
No, it's crazy
Code
things.
is like completely.
So I always mess this up when I'm writing code, but anyway, just keep that in mind, that if you're working with tuples, there'll be ._1, ._2, ._3, on and on. And so for key value
Python
pairs,
is much more uniform.
yeah, Python and R will be zeros based.
It's uniform. It's better.
Okay, so let me cut into a little bit more interesting. That was all the basics. So let's look at some other parts. Michael Armbrust is the lead on what's called Spark SQL and now data frames based on it. And here's a talk that he'd done recently. A few years ago, there was a notion of using Hive with Spark. How many folks have used Hive or seen? Okay, some. So Hive is SQL on Hadoop. And I've set up some pretty large Hive practices. It's very convenient to work with large-scale data and run SQL queries over it. A few years ago, there was a project to take and replace MapReduce on the back end of Hive with Spark. And running across large benchmarks, they were able to see about factor 100, 2 orders of magnitude increase in performance when you had complex queries because you get much better pipelining. And so that had been a project called Shark. And last year, another project went top level called Spark SQL, which took over all of Shark and basically rewrote it, got rid of the Hive code. You can still bring in your Hive tables and HQL queries and use the Hive metastore. You can bring in what you would be running on Hive directly into Spark SQL. But they had problems with trying to work with the Hive optimizer. Most times when you're optimizing SQL queries, you'll look at optimizing a logical plan, optimizing a physical plan, and with Hive, that was it was conflated. So they rewrote it to be able to have a better optimizer, and we'll show some of how this works. At the very top, we have something called data frames. Anybody here use pandas in Python? Some? Okay, so it's similar to that. Distributed data frames. Or data frames in R, of course, if any R users here. No, a few, okay. My teams have used a lot of Python and R, and data frames are a really convenient abstraction for describing a data set and how to query it. So Spark has had this notion of a distributed data frame, and it's at a higher level, and there's RDDs underneath. You can always get to the base RDD. But with the data frame, it's a lot more convenient to program, and it gives expressions that are much like you would see in Python or R. And also, you have a lot more metadata, so there's more room for Spark to optimize under the hood. There's something else called Data Source API, which says there's a small API where you can use a cost-based optimizer to hook up other types of storage frameworks. So, for instance, you could write a Data Source API out to Cassandra and then define how to optimize by taking, for instance, filter scans and pushing them all the way out to Cassandra.
Cassandra is a key value store that is used quite.
Yeah, it's a popular one out of DataStax. So data sources, it's really just a few lines of code to hook up to most of the distributed frameworks that we've seen so far. And I can point you toward some good examples. We just did a tutorial with Huawei at OSCON 2 weeks ago about this. Catalyst is the cost-based optimizer that's being used. It's a separate standalone project. It was created for Spark, but it really takes advantage of the lazy evaluation. Parquet. How many folks have used Parquet as a storage format? Some. So I have another slide on that, but Parquet is a way of leveraging column storage. And it's really a best practice for Spark, especially when you're working with data frames. I'll show an example of it. And then down at the base, there's something called Tungsten, Project Tungsten, which I understand in Swedish is pronounced Tungsten, Tungsten, heavy stone.
Who chooses the name?
I think Ali probably.
Ali,
yes.
okay. So Tungsten means heavy stone in Swedish, no?
Tungsten, well, I have a few slides on this. What's interesting is that by having all this stack here, being able to do SQL queries out of data frames, but then all these other pieces, when you get down to this layer, you can actually take a lot of the data and move it off heap. So Spark is moving much of its data management off of the JVM heap, and that way you can get rid of the problems with garbage collection. There are other properties as well in terms of code gen and being able to actually move computation outside of JVM onto GPUs, for instance.
So if
yeah.
you were running in .NET, you wouldn't need this thing because you can do managed memory already in C#.
Well, you know, we could use a CLR or KVM.
Yeah, exactly.
We could use a bridge and
Yeah, exactly.
go pay. Anybody ever done that? Anybody ever run? Okay, that's even more interesting. If you have a SQL query, here's kind of the pipeline for optimizing it. If you've got a SQL query, then we'll get down to the template, basically parse it. Or if you're doing an operation on a data frame, you'll get that pretty much automatically. You'll have the logical plan, and you have the catalog of all the different data sets that you want to work with, the different data frames. So we'll resolve the logical plan and then optimize it, move predicates around, and then we'll create a physical plan based off of the cost model in the data sources API. Then we can choose the right physical plan to be able to leverage all these different storage frameworks. So what this looks like is if I have a query here, I'm going to take two different data sets. One of them is just a raw file. The other is some sort of table say it's in Cassandra. If I take these two and join them and then filter on the results, basically if I have a select with a join inside of it, this is what it looks like logically. And so the graph that you initially get in Spark would look like this. But as we run the optimizers, then we'll map from a logical plan to a physical plan. So for instance, here we can take the filter and move it down a level because if we actually look at the query up there, the filter only applies to one side of the join. So that's one optimization. And then we can go further. We can say, actually take this and move it all the way out to the framework by doing a filter scan. So there's a lot of room for doing things like predicate pushdown, as I described, and also with Parquet or Cassandra doing things like column pruning. Let's see. So yeah, Parquet. If you haven't seen it, here's some pretty good links for it. Julian Ledem at Twitter has been one of the leads on this, and here's a pretty good talk. Suppose you have a record that has 50 columns, and you're doing a query against that data set, and you only need to query 3 of the columns. What Parquet says is, number one, it's a column store. So in a given column in your data set, you'll probably see a number of values being repeated. So there's opportunities to compress it better by doing a column organization. Number two, because it's a column store and it accepts predicates, pushdown predicates, then I can say, okay, only deserialize and decompress the 3 columns that I need. Ignore everything else. So you get a really big win on the amount of compute required to do the deserialization. You don't have to bring all that data up into Spark and then filter it. So the column pruning is a really big win. That's why we definitely recommend working with things like Parquet or other types of column stores that are smart like this. There's also Orc. There's another competing standard emerging out of Hortonworks that's like Parquet. And I've seen a couple others being proposed as well. Okay, so I've got an example of how to work with this. There is, if you want to work and do this as a homework assignment, there is a file that's loaded up on Databricks Cloud, and it's all of the user email forums messages for Spark. I've got one JSON file that describes January 2015, all of the Spark user email list. And we can try to do some queries on that. But I can leave that as an exercise, but I can also show you if you want to punch down and see exactly where this is. If you go into Exto, I've got the data loaded up here. And it's, I've got like 6 months of the Spark email list. They're JSON files. And then if you go here, is an example of running this. So I can say SQL context. It's a wrapper on top of Spark context. And basically off of SQL context, I can run JSON file, load in a large JSON file. So I'll give it a path, and I'll say cache that. And I get an RDD there. Now I can take that and register it with a catalog. So I can take this RDD or data frame and register it with a given name, and then I can run SQL queries against it. And one of the nice things with this is that when you've got JSON,
You can run it, right?
yeah, I can run this.
You just want to see how many counts. The count is there.
Oh, see if it's changed. Sure.
Runs. Good.
Yeah, I just run that before. So it was like 13,000 messages.
Yeah, 15,000.
Yeah, I can actually show some examples of this for graphics. I'll do that on Saturday for part of the ML lib. But you can see that a raw message in JSON, well, it looks like JSON. It's just a big string with line separators. But once Spark reads this, it's able to grab the metadata out of JSON. So if you take a large JSON doc, it'll do a union across all the different records and synthesize a schema. So I can take this message and do print schema, and now I've got some schema I can query against. And that works with nested tuples as well, or nested data structures inside of Java. JSON. Anyway, you can look through this if you want to see more examples, but this is a way of creating data frames and then running SQL queries against them. So for instance, here's a way of using functional programming to say who are the most active senders in the Spark community. Or alternatively, you could do this as a SQL query, which is much more compact, and it actually gives you much more opportunity to optimize. So I recommend using SQL. As it turns out, Sean Owen is there every day, just about. He's from London. He's from Cloudera.
Who is from where?
Sean Owen is a chief data scientist at Cloudera.
Cloudera.
Yeah, and he's the most active person on the email list. He's not doing anything else. I talked to him about it. Just kidding. He's a great guy. Michael Armbrust, who is actually the lead on Spark SQL, is number 3 so far.
Oh, yeah.
We're actually trying to understand some community analytics this way. So anyway, if you want to take a look at some examples of different types of queries, transformations to be able to develop leaderboards about this community, we've got a bunch here. There's one person who has answered his own question
One question.
36 times. So he definitely has the answers. So anyway, there's if you follow along here, there's also some natural language processing and then some graph analytics. I use an algorithm called TextRank. It's basically, if you do a little bit of NLP processing, parsing the sentences in the email messages, and you tag the words for part of speech, then for any given paragraph, you can construct a graph, and then you run PageRank on the graph, and you can find out which noun phrases are most highly ranked. So it's a way of doing automated document summarization. It's better than doing like n-grams for understanding like keyword analysis. It's much richer. So here's a way to do this in Spark. Anyway, so those are some examples of running with data frames. I had another one that's real compact here. If I just take 1 month of the email list, I'll create a data frame out of that, loading in the JSON file. And like I said, you can print schema right away. And now if I take that data frame, rather than doing a SQL query, if I leverage the way that, say, Pandas or R uses data frames, I could just do a quick function on it here. So I can say group by sender and then count. And this gets translated the same way SQL does down into functional programming. It's yeah, like I said.
Filter and then show.
Yeah. So this would be similar to using Pandas. Give you pretty much the same result. Okay. Now, Tungsten. So here's a good talk about this. There's a video that goes along with it. Josh Rosen is one of the leads on this, and talking about getting closer to bare metal, moving away from garbage collection. So with Spark 1.4, which is the current release, there are early features of Tungsten. They're still marked experimental. Most of them are turned off by default. But a few things that it's doing currently. Number one, it has a new shuffle service, a new kind of shuffle manager. We're actually backing away from some of the use of Akka and moving towards using Netty for some of the services. So you can think of applying microservices inside the cluster, really. You get better performance on that. There's also, because of data frames, we have more descriptions about the data sets. So we can actually do serialization better than the other kinds of like cryo or other serialization formats. So we're able to optimize that and do better compression of the data as it's moving across the network. And then from there, Tungsten is doing off-heap management of memory, so getting rid of garbage collection, being able to use really large memory spaces with multi-core processors, but not have the liability of JVM garbage collection. And another thing is code gen. So if we're taking a look at a query and optimizing a query, and we know that we're going to take some of the predicates and move them out to another distributed framework, say like Cassandra or Parquet or whatever, then what we can do is actually generate the bytecode for that query and just push out that code as it's generated, which means that the other framework won't have to interpret, and it makes it much faster. A lot of compiler optimization then. Also, vectorized record processing is a way of leveraging GPUs. And the main thing is being able to exploit data locality in the processor caches. So I think this is a good way to say it. This is actually a drawing that was on the board at Databricks to describe it. But when you look at a hash map and how many memory calls, basically how much memory has to be managed, this could be translated in off-heap into a key value pair over there just in a binary map. So what this means is that if we have data frames in SQL, Python, Java, Scala, R, etc., we can do a lot of optimization here, and then we can run on JVM, but we can also run, in the long run, things on GPU, LLVM, etc. So Tungsten is basically something on the roadmap, but we're starting to see some features for it now. And when we do see, I don't have a good slide for this here, but one of the issues is that when you run Python, it is slower than running Scala because there's more memory communication between Python process and Spark. If you use data frames, we can actually make all of these languages run in the comparable amount of time.
How come? What happens with the Python interpreter?
So what happens there is, again, we're doing a lot of code gen. I mean, the Python parts, say you're running, I don't know, Seaborn or some kind of Python library for visualization. Let's discount the last mile, the visualization part. But when you're doing a join in Python, all of that now is effectively being generated as Scala code and run in a very efficient way with Tungsten, such that we see parity for the runtimes for large-scale joins, say in Python, R, and Scala. So we think that in the long run, this really is a much better way to go. Patrick Wendell has some great talks about this, also Reynolds, Shen, and others. So I'll defer to them somewhat. Let me go into Spark Streaming. How are we doing on time here? Yeah, we got time. Okay, good. So,
12:30, so it's
okay, great. So Spark Streaming, anybody used Spark Streaming before? Some folks here? Okay, great. I've got slides from a much longer talk. I think it's one of the most interesting parts of Spark right now. Certainly when we look at use cases, it's where we get a lot of the adoption from enterprise, large customers. So I have more slides than I can really cover here, but I'll leave those if you want to drill down on it some more. Okay, so Spark Streaming, we're going to consider the following requirements. We're talking about clusters that go up to hundreds of nodes. And frankly, if you've got a streaming cluster, we rarely see it go beyond 100 nodes. The cluster overall, the Spark cluster, may be quite large. We've seen Tencent and Alibaba, some of the large installations in China have 8,000 nodes per cluster. Very, very large. But the streaming part of it is probably only 100 nodes. And that's fine because you probably don't have 100 different streaming channels coming in. We'll take and stream in the data into the streaming portion of it, and then downstream we may do some analytics on a larger cluster. Part of the problem with streaming is that you have to understand within a very tight SLA if any of the nodes in your cluster are no longer working. And the only way you can determine that is across the network. So if you have a streaming cluster with really tight specs, it becomes almost impossible to figure out which parts of the cluster are still responding or not because of TCP. I have seen I've seen research projects out of Spain where they were removing TCP from the network stack and replacing it with much more high performance alternatives so they could bring these windows down. Now the latency for Spark streaming then is defined as 500 milliseconds or more. Typically we see windows on the order of seconds. We've seen a few cases where they could get below, like I said, that one research project in Spain, but usually half second or more. And for the kind of use cases that we're going after, that'll meet most of them. The big emphasis here, though, is about efficient scheduling and efficient recovery from failures. That's really where the emphasis for Spark streaming has been. And I'll show that in much more detail. One of the driving factors on Spark streaming is that we see a number of companies where they'll take the same business logic and run it at least twice. Once when the data first comes in and it's on the wire, and then subsequently in some type of reporting. So there's a need then to blend the real time and the batch. The way that this works is based off of what Google called microbatch in Millwill. You take the live data stream and split it up into microbatches of some time period. And then each microbatch is handled much the way that Spark would be running a batch job. Now, you can bring in sources from all kinds of different types of receivers. Some of them that are built in, you could be reading off of Kafka or Flume. You could read off of message queues. We have some utilities to read off of Twitter. If we have time, I'll try running a Twitter example. And so there's a number of these that are available. And I've seen a number of adapters. I've got another demo that uses TCP sockets just to kind of debug things. Has anybody here seen Millwill before? Some? Yeah. Okay. So this is a great background reading. Tyler Akido out of Seattle is one of the authors. He's done some great talks at Strata Conference and others. But Millwill is what Google uses internally for stream processing, very similar to Spark streaming, although Millwill is much more mature, has much better semantics for how to clean up jobs that are long running. If you can catch some of Tyler's talks, I highly recommend it. This project is about 2 years younger than Spark proper, and so it started out in 2012. And it was put into Spark 0.9 last year. The main paper here is about discretized streams. So you'll probably hear that mentioned, or D-streams is the shorthand for it. But Tathagata Das is the project lead. And there's a number of people who have been contributing. I wanted to point out some of them to follow. Definitely Gerard Mas at Virdata in Belgium, David Morales at Stradio in Madrid, a number of others. Actually, some of these people have moved on, but there are great use cases for all of these. There was a blog post recently, I think actually just a few days ago, where TD, Tathagata Das, and Matei and Patrick Wendell go into a very nice description of what their roadmap looks like for Spark streaming. And so they have some good definitions for what they're trying to accomplish and how it compares to other types of streaming processing. I'll leave that there if you want to check this out in more detail. TD has excellent talks about this. He usually does a couple of talks a year at Spark Summit and Strata Conference.
There's a lot of talks you can find on YouTube. for
Yeah,
this.
ton of stuff there. For instance, here's one at Strata in the spring.
Sorry, I have a question.
Yeah,
So in a Spark, you're using lineage graph for fault tolerance, so, right?
right.
And in the worst case, if all the RDs must crash, so we end up with the storage and we start from base cluster, right?
So if all the workers, yeah, worst case, the
Yes.
cluster's gone.
Yeah, yeah.
Yeah.
But in the Spark streaming, so since actually there is no storage, so we have to keep
Ah.
the data in the storage. But for how long do we keep it in the storage?
Great. That's an excellent question about streaming because streaming is really complex. I mean, there's a lot of moving parts. There's the sender receiver on the pipelines. There's the cluster managers, the drivers, all this. So what the work that's been done between Databricks and also some of the other partners, Cloudera has been very active in this, is actually to break down the different types of failure cases and then harden each one of them. I'll go through some illustrations that show that. In fact, there is storage associated. So that's kind of new, but using things like write-ahead logs and checkpointing, leveraging a number of different features just to try to go after each possible failure mode. I have some case studies which I think are really important for streaming because they show where the trade-offs are. We see a lot of it in terms of telemetry for data center operations, a lot of online marketing, ad tech, of course security, and a fraud. Telecom, I guess, is much more like a data center operation thing. Video analytics, actually the first commercial production use cases for this were all in video analytics. So initially, Oyala had done a lot of this, and also blanking.
This company that is
Jan's other company, yeah, they were actually the first one to do this in production. Conviva. So Conviva does network optimization for YouTube. If you ever download a YouTube video that's large, you'll see Conviva network access. And they were the first ones to really use this. So when you've got video analytics, you have to do a lot of complex work on networking, as well as transcoding of the video formats, and then also just measuring usage, billing, things like that. So video analytics tend to work with this pretty well. Let me show an example program. So up at the top, we'll bring in a couple of imports for streaming. And there's a variable inside there that says SparkConf. Consider that to be the same as Spark Context, just a different name. So what we're going to do is take Spark Context and wrap it with a streaming context. And then we're going to give it a window, a microbatch window of 10 seconds. This will create a new streaming context variable, SSC. And then to start things off, we'll have to create a receiver. So here we say ssc.socket text stream, and we'll connect it up to a TCP socket. So we'll give it host IP and port. Any data that comes off of that socket for each 10-second microbatch window, that will create a new RDD. And so the RDD is called lines, or rather the whole D stream is called lines. It has RDDs inside of it. So this logic here, these 3 lines are word count. It's just like the word count that we had before in Scala. So what's happening is that for every microbatch window, for all the text coming across this socket, we'll split it up into 10-second windows and run word count, and then print out the results on the console.
So lines really is one RDD.
It's actually
Otherwise doesn't make sense, isn't it?
So formally, you can think of this as a long-running process, as a service. So lines is formally speaking a discretized stream, a D stream.
I see, it's a whole stream.
Right. So inside of lines.
So how come that when you count only for a batch?
So what happens then when you look at the state machine that's running in the service? Every 10-second window, there'll be a new RDD inside of the D stream.
And that's the one that...
That's the one, yeah. So it's a little bit of a shorthand, but that's how it works out. But now when we talk about Spark, we talk about lazy evaluation. Nothing happens until you get to an action. And in this case, the action would be print. But with streaming, it's different. There's a state machine running. And so nothing happens in a streaming app until you tell the streaming context start and then give it a callback for await termination. So this way you can have some control outside to bring down the streaming app. I've got more examples, but any questions about that? Okay, I wanted to point to, this is an excellent tutorial by Gerard Mass, and he's at Technicolor in Belgium. Technicolor has a division called Verdata that does IoT, so they use Spark Streaming for their solution. They do very large-scale work. They're partnered with IBM, and so they have some of IBM's larger customers working on like truck fleets that have sensors on them, things like that. But what's interesting is this kind of architectural pattern that Gerard points out. We see this repeated over and over. When we see the large-scale commercial deployments of Spark Streaming, it uses this pattern over and over. So there are pipes coming in, distributed pipes on Apache Kafka. And so that's a nice way to be able to scale out managing your pipes and have those be robust. And then we've got Spark Streaming running to do some kind of analytics in memory. And then we're using Cassandra for the backing store, for distributed writes, effectively, off of the streaming analytics. So those three being used together, we see over and over. Generally speaking, we also see Mesos. Most of the large-scale Spark Streaming applications that I've seen tend to use Mesos as a scheduler. There's a few that I've seen now based on Yarn, but Mesos gives finer grain scheduling on a cluster. So people tend to gravitate toward that. And as an example, Netflix uses this kind of pattern for some of their work. There's a great article here. Are you familiar with Chaos Monkey that Netflix has done? So they'll take applications and then they'll point Chaos Monkey at it just to destroy them, find out where the failure points are. So they built this really large streaming pipeline based on Spark Streaming, and then they created a new kind of distributed Chaos Monkey for it. And it's really interesting because they could measure for the different features, the different configurations of Spark Streaming, they could find out where the sensitivities were. So for instance, they found out that some of the features, there really wasn't much sensitivity at all, but for others, there was a whole lot of risk. And if you look at it, it's a great article. If you're studying about streaming real-time analytics, I think this is an excellent article to study because they go into describing different types of failure modes and what kind of features for resiliency you can use to try to provide high availability. Actually, some of the authors here are friends. We'd worked together at a previous company. So on that note, we took that, working with Netflix, we took that to try to illustrate where are the potential failures if you have a real-time app. Because real-time apps are, number one, much more complex than batch apps, but number two, much more in demand in industry. I mean, at this point, in industry, we know how to do Hadoop. We know how to do batch jobs. That's pretty well known. But there's a lot more value for getting the real-time pipelines. And so it's worth it to go to the extra engineering effort to make these fault-tolerant. So for instance, consider that you have a number of sources feeding into a cluster. You've got the sourcers, and then each one of these will have a sender, something that's taking that data as it comes in and putting it through a pipe. This is probably something like Kafka or Flume or ZeroMQ, but some type of distributed pipe. The senders then will be paired with the receivers. So out on the Spark cluster, you're going to have a number of receiver processes running. If you're familiar with Hadoop and the notion of a slot, like there's a map task or a reduce task, In Spark, we have these different executor slots running. We could run things. A receiver will take up one of those. So when you're running Spark Streaming, you actually take up an extra process. Now, what's interesting is, just even in the sender-receiver pair, it's really complex because either one of these can fail, either one can overrun, a number of different failures just there. There's also the worker nodes in Spark. The executor process that Spark is running, of course, it's built to have fault tolerance, but it's still complex to manage that. You don't want to lose the data. So when the data first comes in here, we'll replicate it in memory. Also, we have something called write-ahead log, and we also have an issue of the actual cluster manager being something that could be lost. So we have to have ways to restart if there's a driver failure. So if I break this down, first off, just looking at the senders, we have a problem with flow control. It could be the senders send too much data for the cluster to use, in which case we have to communicate back to the senders to throttle how much data they're sending. And this is a hard problem. It's called back pressure, typically, in the literature. And back pressure is a way of describing how these different components in a distributed pipeline, how they can talk with each other and basically control the flow. If you're familiar with TCP, flow control is a hard problem. If you're working with distributed systems and a lot of different frameworks tied together, it becomes a much harder problem. So this is an active area of research in computer science, how to manage back pressure. And Spark has been working with other projects on this. Notably, Kafka is probably one of the more advanced ones. On the receiver side, there's been a lot of work. Actually, Pearson Higher Education has a project where they use Spark Streaming and graphics, a few other things. They do a real-time graph of their sales, basically, people who are using Pearson products around the world. And they were using Kafka, and they contributed some code to help make that more durable. But the idea is we're hardening the receiver. You pay a little bit extra overhead on the receiver side, but then you have guarantees that any data that comes into it won't be lost.
You replicate the patches, I guess.
It's more of the protocol of how it's talking to the sender, but then, yes, it also has the in-memory replication plus a write-ahead log. That's a little bit further downstream, though. It's actually right here. So one of the things you can do is that as soon as you get data coming in across the receiver, you can write it to disk. And so that way, if you lose a node, you can pick back up. You haven't lost the data. So write-ahead logs, initially that was hardwired to go into HDFS, but it's being abstracted out to another API now, so you can write it out to, say, Cassandra. The other thing is that you could lose a driver. The cluster is working fine, but the actual client-side driver, for whatever reason, dies, or the network dies. Yes?
For the write-ahead log, doesn't that hurt latency when you go to disk?
Does it incur latency? It could. I mean, it depends how it's being managed. So all of these things come at a cost. There'll be a tax. So it's a matter of how much durability do you want versus the cost. But if you have a larger cluster or better hardware, then you can manage that more, usually. The driver, you can lose a driver, but since Spark 1.1, we've had the ability to do a driver restart. So you basically checkpoint metadata for a cluster, in which case we can bring things back up rapidly, hopefully without losing data. The other thing, of course, is that Spark is originally based off of Mesos and then moving into Yarn. There is a notion of having high availability for the masters. So if you're using Mesos, the masters typically run in a quorum. You'll have 3 and have Zookeeper to help manage the leader election.
The replicated state machine.
Yeah, replicated state. Or you could use a Paxos kind of thing if you really wanted to.
It's basically Paxos.
Yeah, light. Paxos light. Ben Hyman has some great debates on that one.
Just small variations.
Another thing is that, of course, Spark has always had this problem of executors being lost. How do you manage that? So worker relaunch and executor relaunch is something that Spark, of course, has been doing for a long time. But what I want to underscore there is there's a lot of moving parts. This is a very interesting thing to try to do in the general case, and solve for a number of types of cluster managers, a number of types of pipelines. I mentioned before, we typically see Cassandra, Kafka, and Spark used together. Here's some examples. I'd point to Helena Edelson out of DataStax. In particular, she had some nice tutorials on how to do this. Yeah, if network is running. She had some good Scala examples. We also see Elasticsearch being used a lot. So Elastic produces Elasticsearch as a scalable way of using Lucene. And so if you've got a real-time app and it's computing something that's of value, you might want to take the results and drop those into Lucene indexes to be able to query them later. That's a very typical kind of pattern. And here's a NASCAR slide, as we would say. But there's a number of production use cases. The number's up now to over 90 known production use cases, some of them quite large. Netflix is probably one of the larger ones that we can reference. StratioDB, I would recommend. If you're interested in this area of real-time analytics, this is a company based in Madrid, and I've worked some with them. Very sophisticated use of Spark. One of the things that they did was to take and put a CEP engine, an open source complex event processing engine, on top of this pattern. What this means then is that you can use Spark Streaming to get your data aligned. And Spark Streaming, the streaming is all based off of time-based data. It's based off the timestamps coming in. But by having CEP on top, you can do much more advanced queries. So it could be that you're looking at a data center and you have a number of sensors coming off the data center, and you want to query across different things within some region, some time-based, some period. CEP will allow you to do much more complex logic on that.
What is CP?
Complex event processing. So in enterprise, this is fairly well established. If you want to look at understanding faults, and you have a number of data streams that you're analyzing, you want to run queries across all those data streams, and you want to say action A led to cause A led to event B. So how can you query that? And it'll be across time and across different streams, other things that may parameterize it. And so there's a variety of different semantics that are involved here, but there's a nice open source query engine for that Stratio put on top. I know that BBVA and Santander, some of the other large banks are using this. Pearson has done a lot of work on this, and Dibiendu in particular has contributed a lot of this code back. It's fairly sophisticated work with Kafka. They're also using GraphX at scale. Guavus is a large telco analytics company in the US. And so for North America, they're handling, it's 4 out of 5 of the top mobile operators. So approximately 50% of the US mobile data traffic, and it's 2.5 petabytes a day coming into streaming apps. For them, latency is very crucial. They were able to get this running. Eric Carr is VP of Engineering, and he does some great talks about this, but it really, from the enterprise perspective, they used to think about taking the data and storing it and then applying queries later. But now they've moved their thinking to analyzing the data first and storing it secondly. So they really analyze on the wire, which is a very big organizational change. It's a very big mind shift for how they approach analytics in a telco.
That's interesting to notice as a student that real-time analytics is becoming more and more important now in commercial applications.
Yeah.
Thinking of companies and startups.
Yeah, definitely the telco cases. Ericsson here, of course, is another example. Here's a small company, but very sophisticated. It's called ShareThrough, and they do ad tech. They have a bid system. What's interesting is that they are using streaming algorithms. Was there an earlier lecture about doing probabilistic data structures, approximation algorithms?
No,
Not yet?
it was not yet.
But it's coming up.
It's coming.
Okay, good. So Algebird is a library. If you haven't seen it, I highly recommend. This is really fascinating stuff. there's a library that came out of Twitter, and Avi Bryant, who's now at Stripe, and also Oscar Boynkin, who's still like lead data scientist at Twitter or so. They came up with a scaling library for leveraging type safety in Scala and being able to do a lot of abstract algebra. And it applies really well for doing large-scale linear algebra.
It's like NumPy then?
Yeah, I mean, not exactly. I mean, NumPy is more about computing the numerical side of things. This is more about saying, let's have a library of monoids, leveraging monoids, groups, fields, and their algebraic properties for the functions. So if I know that my function that I'm going to apply to the data, if I know that it's binary and it's associative and that I have an identity element, then I have a monoid.
Yeah.
And so now the compiler can make a lot more assumptions about what that function can do without actually knowing what the function performs. And you can get more strict than that. You can get into rings and groups, fields. And as a result, you can do much better parallel computation. So for instance, one of the things that Algebra would do, a very simple case would be count min sketch. So I can take and look at frequencies on a really large stream rather than having to take a batch window. Instead, I can calculate frequency summaries in stream. So suppose I'm Twitter and I'm looking at traffic coming across. Most of the people on Twitter have like 200 followers. That's the average. But then you get like Justin Bieber and Katy Perry and like, media stars who have millions of followers. So if you're trying to understand how to segment your data and apply advertising, et cetera, you need to understand who the heavy hitters are, who the really frequent users are. Or maybe there's fraud. Maybe there's people who are spamming. And you're looking at certain metrics to try to define, based on frequency summaries, who are the likely fraudsters. So by using count min sketch, you can make this trade-off between the amount of memory footprint for your application versus the amount of error bars. So for instance, with count min sketch, with plus or minus 4% error on your metrics, you can trade off 2 orders of magnitude of memory footprint. So that means you can take a very complex application, fit it all into memory, and run it in streaming, as opposed to taking a batch window. And so because we can get orders of magnitude better performance on this, and also tune it, now we can think of using these approximation algorithms as really a different kind of distributed data structure. Spark is very good for that. And Algebra in particular is a Scala library that gives you a lot of these built in. Hyperlog, count min sketch, LSH, et cetera. So that fits in really well with Spark Streaming. Some of these are actually built into Spark Streaming, but ShareThrough had been the first company to really pioneer this. And they actually pushed back on Twitter and changed some of their libraries because of it. The other thing I will mention is this one here, one of my favorite applications for Spark Streaming. It's from an organization called Code Neuro.
I did this last.
Oh, did you see this one?
I did it.
So,
It was an Amit course on Scala.
yes, exactly, yeah, one of the better ones.
Yeah.
So currently in neuroscience, there's a lot of work around microscopes. For instance, they're doing work out of Genelia and other associated labs, UCSD and others. They can use lasers to look at fish or small mammals, and they can look at tens of thousands of neurons in real time, measuring calcium activations in the neurons. Basically, are they firing? Without cutting the animal open, fortunately. But they can get a lot of data, telemetry, about the real-time activations in the brain. And so the microscope ends up being a lot like these gigapixel telescopes, basically LSST kind of things. But it's microscopes based off of neural networks. So what Jeremy Freeman's lab is doing is they take and put Spark Streaming to process the telemetry coming off of the microscopes, and then they can tune where they want to point, what parts of the brain do they want to study. They can do this in real time. He has some great work on visualizations, and the data rates are pretty large. For zebrafish, which are really simple compared to the rats, it's like 2 terabytes per hour, and that's on an 80-node cluster. But they have this library, I'm going to show in a bit, and they've created a new kind of visualization library for Spark. It's called Lightning. So they have 2 other projects. There's Spark then they created Thunder, and then they created Lightning. And Lightning is a way of handling really general case visualization coming off of Spark at pretty large scale. And at the end of the pipeline, you've got D3 or other types of JavaScript libraries for visualization. It's really convenient. Code Neuro is, I'll show some examples of this, but they're one of the more sophisticated use cases for Spark Streaming. Pinterest is also another one that's came out earlier this year, doing very large-scale work integrated with MemSQL. Uyala on Yarn. I'll leave these here. I don't know if I'm going to have time today, but maybe I can do this somewhere in a hallway.
Still have half an hour at least.
That has some more stuff I want to cover.
Then you can cover it later. Because you
This is a nice, it's a way of doing a language classifier unsupervised off of the Twitter stream.
unsupervised.
So I can show some examples. It is a kind of approximation algorithm. And we've got some code there. It tends to work out pretty well. Okay, one of the things I did want to get to was visualization. So hopefully this is all running okay. In the notebooks, one of the nice things with notebooks, whether it's Databricks Cloud or Project Jupyter or Zeppelin, they tend to have some very good built-in visualization capabilities. So one of the things with Databricks Cloud, it's got the ability to shift back and forth between a table and a chart. So if I'm back over here, let me grab one of these. So if I've got some type of example table coming out, right here. Where's the one where here I have Sean Owen. So I did a query, and I've got this table of the results that are coming out. Down at the bottom, I could take and convert this over into a bar chart. Or, maybe other types of things. I might play around with some of the series groupings, change the dimensions, etc. But I want to show that built in, you have a lot more capabilities for doing different types of visualization. Where am I? Another thing also, you can do pivot tables. So you can do series groupings and pivot tables. There's a lot of different features built in for visualization. Part of it is based around, we have a display command. So if you pass in a data frame, I know it says schema RDD, but it should say data frame. Okay. If you pass in a data frame, you can print it out as a HTML table or results you can pass in. If you have a Scala collection, you can also print that as a table or as a chart. If you're working with Matplotlib, some of the Python visualizations, you can use this to render your figures. So it gives you some programmatic access to how do you visualize. But more interestingly, you can also do display HTML. And so this way you can take the data coming out of Spark into the notebook and then start to use the JavaScript libraries. So has everybody here seen D3? Okay, pretty much. If you haven't seen it, I'd recommend this. D3 is a JavaScript library for doing visualizations. I would definitely recommend looking at examples. And then here they've got a gallery. So let me grab force layout. Dig this up. So it's nice because if you look at the code on this, the visualizations are nicely interactive. You can kind of play with them, change the parameters and all. But more than that, they will give you some HTML code. Let me get a good example here. Like under blocks.org, there's some great examples. So if you want to take and there, okay. So here's Voronoi, interactive Voronoi tessellation thing here. But they've got the code that you can just cut and paste for this too. So for instance, here's the HTML with the JavaScript embedded. So if you want to come up with some pretty complex interactive graphics, you can do that with the notebooks. And what I wanted to show here was that if you look at SparkCamp under Viz D3, we've got a few examples. So SparkCamp physd3. For instance, here I've got, let me scroll down to the bottom. I've got a pipeline that does like character frequency counts over some data. And so I've got a visualization. But the visualization is all in JavaScript, so I can take and change parameters.
It's detached. You're not running the.
Yeah, I'm not. Yeah, I'd actually calculated the data. Remember, there's a separation of state.
I see.
Yeah.
And you have in the browser your JavaScript.
Right. So we've boiled down a result, and now we can visualize it. Or you can do some fancy animations. I think I'd shown a. Yeah, there we go. So if you've got clusters that you're calculating, you could come in here and move your clusters around, do some interesting interactions. Let me see, what else? If you like dogs,
Dogs?
sure. Here's some Voronoi tessellation, somebody's shabu. Let's see. If you want to do some heat maps, this comes in handy. Blam. Of course, heat maps are really, really great for being able to show geospatial data. And if you just want to show all of it at once, we'll take the same data set and run through a lot of different variations on it. So D3 is something really useful. It's a little bit raw, so you might want to use other layers on top of it, like C3. There's a number of these. But I highly recommend what can be done. And more to the point, here at Code Neuro, I was talking about Jeremy Freeman earlier. Matthew Conlin does the visualization for Code Neuro. He also does visualization for a group in the US called 538. They do political analysis and sports analysis. Nate Silver, I don't know if you've ever seen any of that, but it's very sophisticated analytics. And Matt does the visualization for them. So two things here. One is Lightning.
Yeah.
And
Lightning is a Spark library, or was it?
it's actually independent. It was built to work with Spark, but it works with all kinds of backends. And so the idea with Lightning...
Databricks?
No, this is totally open source. This is funded out of the neuroscience lab. It's the Freeman lab.
Okay.
But then they subcontracted to New York Data Company, which is Matt Conlin. So it's agnostic about libraries. You can use it with D3 and other types. And you can get a REST API to hook it up. Basically, it's got Python or Node.js for the back end. So that fits in really well with a lot of Spark. But it also works really well with IPython. So how many folks are using IPython notebooks or Project Jupyter? Cool. Okay, I think I probably asked that question before, but this is where it becomes really salient. They've got some great examples here of what you can do along with the code. And again, this is what they're using when they have, networks inside of a rat's brain in real time, that they're watching the rat go after food and then seeing what the activations are on the routes going to the cerebellum and things like that. It's a really interesting group. What I wanted to show was their actual research. Code Neuro. Yeah.
I wonder if Zeppelin is also supporting this one or not?
I don't know that they're using Project Jupyter for Code Neuro and Lightning. I don't know if Zeppelin has integration on this yet, but it probably wouldn't be hard.
Jupyter would be better to use.
Yeah, Jupyter is more general and it's a little bit more mature. But so what they do is they have a hackathon twice a year in New York and San Francisco, and they get a couple hundred neuroscientists together for a weekend and a lot of beer, and they'll take and work. Basically, the way this research goes, they've got some groups that are funded to collect the data and other groups that are funded to analyze it. And so there's a big problem of being able to share the data and share the algorithms. And so they're using Jupyter. Let me launch this. Basically, the groups that create the data then can publish it in the cloud, along with notebooks that describe how to access the data. And then other teams, research teams, can go in and apply their algorithms to it for what they're specifically looking at. But let's see. Let me try some examples here. Go to NeuroFinder. So I can show you some tutorials here. This is fun. The last one that we did, so here's a Jupyter notebook that they're using, and they're doing, like I say, calcium activations inside of a brain, trying to see what
Do you
type.
use Spark also in?
Yeah, they use Spark to actually grab the raw data and drop it down into something that can be visualized or scored. So
And here is Python, just pure Python.
yeah, for the visualization side, it's Python.
Yeah.
I think they're using PySpark actually for the pipeline, if I recall right.
Ah, but that makes sense.
Usually. So for instance, they're trying to see where the activations are and see if they get correlations across similar activities. It's a really good use of notebooks for repeatable science. And by the way, did you see the Nature article using notebooks?
Nature article using notebooks? No.
Yeah.
Interesting.
So on the subject of repeatable science, I was actually part of this project. I was the alpha tester. It didn't work when we tried it, but a week later, Nature got it running. So what they're doing is they can take an article that they're going to publish and take the code for the scientific article, and then all the dependencies for the code, they can wrap that into a Docker container. And so you've got a notebook that captures the article, but you've also got the code that you can modify, change parameters, and you've got the data. And when they ran this, then I think they had a high watermark of 10,000 people at one time all running these containers, replicating the research. And it was very simple research. But it is an amazing thing for science. And like I say, Spark is being used along with IPython, or Jupyter now, for this point. Anyway, I highly recommend looking at Lightning if you want to do something structured for visualization, especially at scale. And if you're interested in neuroscience, I highly recommend CodeNeuro. How are we doing for time here? We're almost good.
Yeah, you have time.
Okay.
20 minutes.
Good, then I can go into some more demos perhaps. We'll set up for Saturday. One thing I do recommend is Spark packages. So if you've ever worked with Apache projects, getting code committed into Apache is an interesting experience. There's a set of Spark committers, of course, who manage this for Spark. But if you want to do extensions to Spark, rather than go through the whole political process at Apache, you can also submit into this community repository called Spark Packages. And these days, that's what a lot of people are doing because it's a lot faster, a lot less hassle. There's also a Maven repo associated. So if you come up with Scala code or Java code, or even Python code that has a JVM dependency, then you can take and push your compiled artifacts into here, and they'll serve directly out of the Maven repo. And as of Spark 1.4, Spark itself is aware of this package repository. So you can actually do command line options to point to which packages you need to have included. And there's a lot of great stuff here. I mentioned about Lightning and Thunder, they're under here. So for instance, the large-scale neural network analysis that Freeman's lab is doing. A number of different types of connectors. Esri has contributed some geospatial analytics adapters. There's a lot of different things here, so highly recommend it. And as I said, this is being built into the API itself, partly as a workaround. I know there have been some questions about Zeppelin, but there's definitely more integration now with Zeppelin notebooks. Also Spark kernel, which is what IBM has contributed recently, their Spark support, and many others. Another thing I'll point to is there's a developer certificate. If you're interested in getting the developer cert, Databricks and O'Reilly partnered last year for this. So it's a 40-question exam, and a lot of people have taken this so far. I'm one of the authors for the exam, so if you have any questions, I can help answer about that. We have some test prep materials coming out for it. Vida Ha, in particular, has been doing a lot of talks along those lines. Also, Olivier Girardot in Paris. They both have some good materials for that. A lot of the Spark community, the best way to get answers is off the email lists. I've done some data mining in the email lists, the examples shown earlier, but I highly recommend this. There's the user email list for general questions, and then the dev list for people who want to contribute code. And the Spark committers actually prefer that all the questions go there. So rather than emailing them individually, they prefer to answer things on the email list. That way they can get a lot better feedback and also just really collect where the answers are. So that's one of the best resources. There's also a listing of events worldwide that we try to curate, and it needs some updates, but here I'll show. Basically, we've been collecting all of the different talks at meetups or conferences about Spark worldwide. And we do some data mining on that. Try to see some leaderboards based on that. Who's really engaged? I don't know. I may have added a line for this too. I'm not sure if I have this one here. No, maybe I should. I'll change that. There's also a YouTube channel. So a lot of these talks are live streamed. A lot of meetup talks. So if you want to research into any particular topic, the live stream archives typically go to the Apache Spark channel on YouTube, and that's a good resource. So for instance, IBM talking about Spark kernel. Vita Ha talking about data storage tips for optimizing.
Spark kernel, what is it? Is it like, what is Spark kernel?
Spark kernel is a Spark backend for Jupyter.
Ah.
So if you go to Project Jupyter, oh goodness, it's going to give it.
Spark backend, is that done by IBM, you said? Or?
Yes, exactly. So Jupyter is an independent project, IPython. But then if you look back here,
I saw Spark kernel.
yeah, the Spark kernel, that'll go off to the IBM site. So it's a backend.
And there you get it, and then you run Jupyter. Huh?
Yeah, exactly. There's also Spark Summit that I highly recommend if it loads. So Spark Summit is the conference around Spark. We just had the one last month, well, a month and a half ago, for Spark Summit in San Francisco. But end of October, we've got another one coming up in Amsterdam. And so I believe that the talks are all published now for that. Every time that we do Spark Summit, it's been growing massively every time. And all of the talks, the videos and the slides are all archived. So another good way to learn about Spark is just to go back through the archives if you want to take a look at the earlier ones. So for instance, Spark on Mesos. Here's a good talk about that.
I don't think there's academic pricing. It was very expensive.
Really, that's good feedback. Thank you.
It was about $1,200 or something. I'm not kind of
For companies, yes, it's okay. But not
For companies, but not for academic.
No, for academics, that's not really something you have to argue. You know,
Yeah.
That's over the level of what's acceptable.
And these people came out of Berkeley. They should be sensitive to that. Yeah, okay, well, I'll go tell them that. That's a good point. Especially, yeah, that's like 1,300 euros.
Was Wendell, what's his name, the guy that's responsible?
No project
for
would fund that.
Huh, okay, that's good. We should have, I mean, because we typically,
No, but apart from that.
okay, I'm on the program committee. I will take that back and tell them. Scott Wayland is the head of this. But anyway, the archives are a good place to get information. The other thing is I'd recommend there's a series of books. There's a book out called Learning Spark, and actually the code exercises for this are on Databricks Cloud, both the Python and Scala versions. That's written by Holden Corral. She and I have worked together on a lot of projects. She's now at Alpine Data. And Matej Zaharia, Patrick Wendell, Annie Kominski, authors of Spark. There's a more advanced book called Advanced Analytics with Spark. That's out of Cloudera. So Sean Owen, I was picking on him earlier. But these are a lot of the top data science people at Cloudera. And Mahmoud Parsian just did a book recently, Data Algorithms. And these are expressed both in Hadoop and Spark. Also an excellent book. If you want to get a hold of me,
You have your book.
I have-
Excellent, too.
yes, and there's a video also.
It's a video.
It's a video for the intro course that we do at Spark Summit. It has a few other exercises added. We have another one coming out that's a vertical. It's a bundle of all the best Spark talks out of Strata for the past couple of Stratas. That'll be published next couple of months. And also the CERT exam preparation. That'll be coming out. If you want to get a hold of me, there's a sign up for newsletter and how to contact me on LinkedIn or Twitter or whatever. And of course, a book that I did. So there's that. I've got some different examples I can drill down into, but I guess we only have about 20 minutes. So one of the things I should check is any questions in general.
Any questions? Just
Okay. We're going to have another talk about machine learning,
yeah.
and that'll be Saturday
Yes.
afternoon. So we'll go into MLlib and GraphX.
Exactly.
And I have a number, if you want to see a flavor of that, we'll be working off of some of the libraries here, BikeShare and Exto.
Yeah, you can load into your own.
Yeah.
directory.
And also, if you're familiar using the Iris data set, Reza Zadeh and I both did some implementations on MLlib based off of Iris data. Okay, having said that, thank you very much. Call it good?